Hello my friends, this is lecture 4, going over the concept of electric field again, and electric field lines, and how does it look in capacitors and conductors. Capacitors mainly charge in two plates, conducting plates with two different charges, one negative, one positive. We can easily do this by connecting them to a power source, a battery for example, and we can charge them. Then we can take them away and use these charges. They will generate a charge separation, and we will have an electric field shown in here from plus to minus parallel plates. If we want to think about the details, we can calculate electric fields at a point from all the charges along the capacitor, plus minus, add them. We will have electric fields away from pluses towards the minuses, so it will be all upward in here, and X components will cancel. We'll have overall upward electric field, and it is also given us parallel electric field lines and uniform throughout inside the capacitor. We can calculate this electric field by dividing the charge of the capacitor by the area times a constant, what we call permittivity of free space, and here is the value of it. That's how much we're going to talk about parallel plate capacitors at this point. And this is all summarized in here. Uniform electric field lines, plus to minus, and here is how we can calculate it. Going back to electric field of plus and minus point charges, we said it's always away from point charge and towards the plus charge, and towards the minus charge, and it's larger closer to the charge, smaller farther away. We show the electric field with electric field vectors. Here we are seeing we can also show them with electric field lines. And how electric field lines tells us information is that if they are closer to each other, we have a stronger electric field. So closer to charge, we have strong electric field here. Let's call this E1. Farther away, the lines gets farther apart, we have smaller electric field. So we can safely say E2 is smaller than E1. Going back to the equation we discussed in lecture 3, we know that as we go far away from charges, R gets larger, E gets smaller, inversely proportional. This question here is talking about an electric field inside a parallel plate capacitor. This is actually used in long highways, tunnels, to clean the air. What they do is they charge the dusts, and they have parallel plate capacitors here. One is positively charged, one is negatively charged. And they charge the dust as the dusty air goes through. Negative charges would accumulate on this positive plate, right? Opposite charges attracts, and positive charges would accumulate on this negative plate from the air. So we have dirty air going in and clean air coming out. How cool is that? That's our physics. Now this question is about that. Long highway tunnels must have air cleaners to remove dust and soot coming from passing cars and trucks. In one type, known as an electrostatic precipitator, air passes between the two oppositely charged metal plates as in the figure. The large electric field between the plates ionizes dust and soot particles, which then feel a force due to field. This force causes the charged particles to move towards and stick to one or the other plate, as I described, removing them from the air. So a typical unit has dimension as shown in the figure. What is the electric field between the plates? Charges are given. This would be our Q here, 540 nanocoulomb. That would be 540 times 10 to minus 9 coulomb. And the length of the sides at 20.6 centimeter. I'm going to convert this to meters. 0.206 meters, and the other side is 38 centimeters, so that would be 0.38 meters. Divide by 100. The distance in between is given, but it's not relevant here. We'll calculate the electric field of a capacitor known as charge and area using this equation. We know the charge. We don't know the area, but we can calculate it easily. Sides multiplied with each other. We'll have this value input in here. And epsilon is our constant, permittivity constant. And put in all the values. We'll have 7.79 times 10 to 5 Newton per coulomb for the electric field. As for the direction, it's always from plus to minus. So this plate is overall all plus, this plate is minus. Electric field will be in this direction, to the left, as described in here. We already talked about electric field lines, but over here I want to discuss on this figure how we use. If I know a positive charge, I can already imagine electric field decreases as I go away and so on, and I can imagine its direction. But sometimes I might be given electric field lines only, and I might need to decide on things on those electric field lines. So what do I do? Excuse me. First of all, along an electric field line, electric field direction is always tangential to it. So to find the electric field value along an electric field line, I can draw tangent lines. This one is drawn for me. Of course, I didn't do a good job here, but we can try to move it a bit. That's my electric field there. I can draw one more here. Tangent, another one, already drawn, and so on and so forth. So that would be the electric field direction along the electric field line, always tangent, and it will change. So I'm going to call them E1, E2, E3. How do they change? Is I look at the distance between the electric field lines. If I call this R1, R2 is larger, R3 is even larger, more larger. So electric field decreases as we go along. So if I'm comparing the electric fields here, E1 is smaller than E2, smaller than E3. That's one thing. Another thing I can learn after that is if I put a positive charge, let's say, use it green. Let's say I'm putting a positive charge here, positive Q, all the same charge to different positions. I'm putting that here and here. They will be applied a force in the same direction as the E, and I'm going to call those forces F1, F2, F3. The lengths are not to scale, just symbolically shown. I can easily find which force is larger using this equation we learned before. The force applied to any charge is charge times E, charge times electric field. And we look at absolute value here, keeping in mind that for positive charge, F is the same direction as E, and it's the opposite for negative charge. So I showed it here already. If E is larger, the same charge, right? This is not changing. If E is larger, then F should be larger. So I can safely say that F1 is also smaller than F2 is also smaller than F3. Of course, if I put a negative charge, I'm going to show a negative charge here, maybe minus Q here, there. It will be applied a force still tangential opposite the electric field line, so F. let's call this, I don't know, F1, F2, F2, so let's call this F2, F4, F5. Those are the forces applied to negative charge opposite the electric field, and it's also equal to QE. Absolute value, I generally choose to drop the absolute value, take the charge as positive, and then decide direction using the sign of the charge, and I suggest you do the same. So these F's in opposite direction to E. And that will always be the case. We can be asked to draw electric field lines, and what we do is start from positive and go towards negative. If we have two charges, we know this charge, for example here, this is an electric dipole. If it was alone, it would have electric field lines in this fashion. But there's a negative charge, it affects the results, and what we do here is we curve the lines towards this charge. And what we have will be a dipole, as you see in the figure. This one is an example of how we can draw different versions of electric field lines. We have positive charges along a disk here. Inside we have negative charges inside a smaller disk. We will draw electric field lines from plus to minus, and we'll connect them together. If we have a surface of a conductor, we overall draw the electric field lines perpendicular to that surface. This will get us to the answer, perpendicular. Inside and outside, overall it shows us electric field lines should be straight lines. Two parallel plates have charges of equal magnitude but opposite sign. What change could be made to increase the field strength between them? Let's remember that electric field was plus to minus and uniform. Let's draw some symbolic lines, and it's equal to this equation here. What do I want to do? Increase the field strength. I can look at my equation. Electric field is directly proportional to Q. So this tells me if I increase Q, electric field will increase. Direct proportionality tells me that. Upper arrow I will always use as increase. Keep that in mind in these type of comparisons. What else? This dude is a constant. I have A here. It's inversely proportional to E. So in terms of that, then if I increase A, E will decrease. So I have a decrease in E with increase in the area. I'm looking for increase, right? I want to increase this dude. So what I want to do is either increase charge, or I can do that. If I decrease the area, then E should increase because inversely proportional. So I have two options here. I want to either decrease the area to increase the electric field or increase the charge. Let's see, increase the magnitude of charge on both plates. That will work. Decrease the magnitude of charge on both plates. That wouldn't work. Increase the distance between the plates. Decrease the distance between the plates, not related here. Increase the area of the plates. It works opposite, decreases electric field. So the answer should be A. This here nicely discusses how our hearts work in a way that we have dipolarization as signal comes from the muscles, and it builds an electric dipole. It has an electric field that goes into torso. These are electric field lines. And as we measure electrocardiogram to check how heart is working, if it's rhythmic or if it has any trouble, we actually measure that electric field. Isn't that cool? An electron is in the another example here. We have an electron in here. What is the direction of the electric force on the electron? I'm gonna actually draw these a bit more separate to discuss on this, plus minus. And I'm putting an electron right in the middle here. All I have to do is electron, it has a negative charge, so I'm going to symbolize electron with minus A. And I'm going to look at the direction of electric field, which is always plus to minus, right? I'm going to draw it here too. I have a direction of electric field plus to minus. This is E field. And I know electron is a negative charge. What happens to negative charges? They move opposite to electric field. They're pushed with a force in a direction that is opposite to the electric field, and the force will be up, and the electron will go in that direction. The answer is A. Conductors in electric fields. This is just a very interesting work of nature. Whenever we have a conductor and we charge it, we had some conductance spheres. It was happening there too. Unfortunately, we can't see it with our eyes. But what happens is that conductors pushes the charges around. Remember, in a conductor, charges are free to move. So actually electrons are moving, protons are not. We discussed that. But if you assume protons are also moving, the results will come out the same. So we will assume positive charges will move around, rearrange, negative charges will do the same. So if I charge a conductor with a positive charge, for example, it will rearrange itself in a way that all those positive charges are on the surface, and inside is nice and clear, zero charge. It's because conductors always want to maintain zero electric field inside, so they rearrange charges to maintain that, and that is maintained if only they push all the charges to the surface. Keep in mind, the inside doesn't have to be empty. It could be a full conductor. Still charges will be pushed to the surface. So it doesn't matter if I have a hollow sphere or if I have a full sphere. I forgot the word for that, but not hollow. And I charge them, they both will push charges to the surface. Let's say I charge them negatively, charges will be on the surface. If it's a hollow sphere, actually it will be very outside surface, and full sphere also will redistribute charges to be on the surface mainly. I put some lecture videos on this, how people are using this idea to do some demos and so on. It's pretty cool. Another thing that comes out of that is that electric field on the surface of a conductor will always be perpendicular to the surface. We used this idea in a question already. This question also uses this idea. The figure shows a positively charged metal sphere above a conducting plate with a negative charge. Sketch the electric field. I have to make it positive here, but then it has to curve down. Sorry, not positive. Well, positive, but perpendicular. That's what I meant. Away from positive, curves down towards negative, perpendicular there as well. That's the idea here. I can draw a line like this here, again perpendicular, as long as I have a conducting surface. And you got the idea. This will be more out here and then down. Then again, I want perpendicular lines and so on and so forth. And you have the answer in the next page. Here's the full drawn figure. Idea of electric field is in nature of clouds. Usually clouds charges by friction or conduction. They move around each other. They charge, for example, if we have a positive charge in a cloud, it will try to accumulate negative charges on the ground. When that happens, they become kind of ground, and cloud electric field from plus to minus. It could be other way around as well, like you see in this figure. And if there's a higher surface like this lady over here, it's of course easier to accumulate charges here. And what the clouds wants to do is to discharge through the air. They can't discharge because air is an insulator. It's also called dielectric. More technical form. And they want to build a pad by making it a conductor, build a conducting pad by ionizing the air. And the stronger the electric field they have, let me draw the electric field lines with red. If they make strong enough electric field, it will be strong enough to push on the molecules in the air and ionize them, free some electrons, and build a path and move its charges to the ground. And this, my friend, is what lightning is. So if you're outside, you're an easier target for the clouds, so don't stay outside during a thunderstorm. This is about Franklin's kite experiment. Benjamin Franklin, as you perhaps know, worked on charges and electricity a lot. He's the one coming up with plus and minus charges, to my knowledge. He predicted that lightning has electricity. And he tested that by flying a kite during a storm, putting a conducting key here, and accumulating charge in a Jayden jar, which was kind of like a parallel plate capacitor. And he proved this way that lightning has electricity. Now we know that, but we didn't know it back then. And this is the explanation of how the lightning is ionizing the air and moving down. Since the lightning wants an easy target, after Franklin's experiment, actually, we came up with the idea of what we call lightning rod. In big buildings, they are a good target, for example, for lightning. So we put lightning rod, which takes the charges and moves them down the ground without harming anybody. And that's what this part is about. Faraday's cage is the demo people always use. So if you have a conductor, it doesn't have to be, again, a very thick surface. This one is like a cage, very thin surface, but if you charge it, this is the Faraday's cage. I don't know if it's true, but rumor says that Benjamin Franklin used Faraday cage in a party to impress people. So he would went into the cage and let people zap him with lightning, like this big electricity here. This is from a museum, I believe, from Boston. I wish I can go one day. And he would show that he's not killed, because inside the conductor it will be always nice, no electric field, no charges. One very good professor, Walter Lewin, also shows this in his class. I put a link to engage, watch that. He even touches the interior of this cage, which is very dangerous. If your finger gets out a little bit from the empty parts in here, you could be zapped. But they generally make these cages in a way that you can't really poke your finger out. If you do, it won't be good for you. But inside is nice and clear and no electric field. Because of that, if you are outside, you're caught to a thunderstorm, you can't go home, go into your car, because it is a conductor and it will keep the charges on the surface. You'll have a nice and calm place in the car. Faraday also has a very interesting experiment as he come up with this idea of conductors having charges on the outside of the surfaces. So if you have a conductor not charged and put it close to an electroscope, electroscope's leaves should be closed if nobody is charged. You put a charged object closer to inside of the conductor. If it's positively charged, for example, it will attract negative charges towards, and outside will be positively charged. And the leaves will open. If you move it away, leaves will go back. If you touch the positively charged sphere to your conductor, it will share the charges, right? They will share the charges. And the charges will go outside of the conductor. Leaves will still be open. And now you take away your sphere, leaves will stay open. What is interesting here is that inside will have zero charge. So if you touch your electroscope, inside, if it's possibly charged, you touch it, well, nothing will happen, or because neutral. If you touch your electroscope, neutral would be a better idea because it will give you more information on how inside is not charged. Neutral electroscope, touch inside, outside positively charged, electroscope leaves open. Inside, nothing happens, leaves stay the same. This is not very easy to get working because we have humidity around and so on, but it's pretty cool experiment. Alright, see you.